Okay, hey, Opposing Gloves here, and today we're going to be taking a look at what does it mean to say log, let's go to black, log base b equals x. You know, what does this mean? We need it for decibels, we need it for when we're converting from Hertz values to some sort of a pitch value. They're on different scales, and so there's various ways I could explain what this means. I'm going to go with the simplest and I think the most intuitive way of understanding what this means. So a logarithm works on a logarithmic scale. And there's different kinds of logarithmic scales, but it is a log scale, right? And this scale is a multiplicative scale. And then there's another type of scale, though, that you are already familiar with. And we can use it to understand how we get to logs. And that is called the linear scale. And it is the scale that looks like a line. It's called linear. And this scale is absolute. It's absolute. What does absolute mean? You know, we'll talk about this. What is multiplication or multiplicative scale? What the heck does that mean? Because I've seen a lot of people use this and they don't understand why they're doing what they're doing. They've just sort of memorized the rules, which is okay, but it's not very useful. So what we're going to do is let's start with linear scales and then we'll get to log scales. It's a very easy way to understand it. There's also a historical perspective. Logs were actually originally used to skip multiplication. It allowed us to multiply very large numbers much more quickly, and they had all these big tables to do it. I think that value has a lot of merit. One day I'll explain it, but in this video we're going to go with the simple version. So here is a line, right? And let's say that I gave you, first we're going to talk about linear scales. So let's say I gave you the equation 1 plus 3, and I said, show me on a line what this equals. And so you using algebra, because it's a very simple problem, you say, oh yeah, it's 4. We know it's 4. But what would this look like on a line? Well, what we're saying is this is a linear problem. So let's write that down. This is a linear problem. So we're moving in absolute values. We're moving in plus values. So let's say, let's go here. Here's 1. Let's say that that's 1. And then we say, well, Mr. Gloves, we start at the point 1, and then we go 1, and then we move a point over of plus 1. That's only plus 1. We want plus 3. So we want 1, 2, and then another plus 1, and another plus 1, which will get us 3 and then 4. So there are 3 plus 1s. And that's where our 3 came from. And then we get our plus 4. We get our 4. Well, not plus 4. We get 4, though. That's our answer. That's how we got it, Mr. Gloves. We moved in values of addition. Plus 1, plus 1, plus 1. And we could do subtraction the same way. We just go backwards. So we just subtract 1, subtract 1, subtract 1. You could also view it as adding like a -1. That's another way of saying it. So not multiplication. So addition and subtraction are very similar in this regard. So let's say that we had whoops, I forgot to turn my line tool on. Let's turn that on. Okay, so let's say that I asked you to express, 3 minus, got to turn the tool off now, 3 minus 2. Okay, well, that's easy enough. We start at the point 3, and then we go plus -1. And so that's how you can view it as addition as well. And so we say, okay, well, we're at 3, and we want to go -2. So here's a -1, and we need another -1 because that is actually, 2 is actually -1 2 times in disguise. And so we get 2, and then we get 1. And that is why we have a plus and -1. So now we're going this way. And that is an absolute scale. We're moving in addition. Well, let's step it up. Let's go up to the next level. So the next level is, well, how could you express things like, like 3 times 2? Because now you could do things up here. You could do like 546 plus 392. You could just keep doing this over and over and over and over. What about 3 times 2? How would that work? Well, 3 times 2 would work. It's interesting. The screen shows more on the computer than what I actually have on my pad. Curious. So we have 3 times 2. How could you rewrite this? Well, this is the same thing as we've got 3 2 times. So we have 3 plus 3, and that's 6. So we can rewrite 3 as addition. And we could rewrite, okay, well, that's 3 times 2 is 1/6. Well, okay, let's do, or you could rewrite 3 times 2 as 2 plus 2 plus 2. So here we notice our number, this 2 is how many of the other number is there. So for example, there are 3 2s, while up here there are only 2 3s, and they both give us the same number. They both give us the answer. And so multiplication, we call this commutative because multiplication can do this. But we could rewrite, let's say we have like 8 divided by 2. What about 8 divided by 2? Well, we could rewrite this as 8 times 1/2. So now we've rewritten our division as multiplication. And for multiplication, we know what to do. We have either 1/2 of 8, which is a little confusing, or we have 8 1/2s. So I'm going to rewrite that one because it's just a little more clear. So we'll have 1/2 plus 1/2, that's 1. 1/2 plus 1/2, that's 2. 1/2 plus 1/2, that's 3, plus 1/2 plus 1/2. And that will give us the answer of 4. Okay, and we have 1, 2, 3, 4, 5, 6, 7, 8. So we notice, hey, we just found out something. We found out that addition, subtraction, multiplication, and division are all on an absolute scale. They can all be expressed as addition. And so if we are moving along on some scale, we move along. And so here's like a scale. And we're moving along 1, 2, moving in some value of +1 or plus something, some unit. In the case of multiplication, let's rewrite our multiplication example. So here we have 2 times 3. And so on our number line, we've now done this, right? We know that this is actually, we're moving in some value of plus. We know this is actually plus. It's linear. What the heck? Lineus? What the heck am I writing? Linear. Okay, so what does that mean? Well, here we have, we know that this is actually 2 plus 2 plus 2, or 3 plus 3. And so we say, okay, these are both 6. Well, what if we started at 2? Let's do the 2 example. Well, then we'd move it plus 2. That would put us at 4, plus 2. That would put us at 6. Or let's do the other one. Now, let's say we have another number line. And here we have the value 3. And we move at a value of plus 3. And we get to 6. And if we were to keep going, we could continue to go and derive all our multiplication tables using number lines and the fact that we're moving on a linear scale. This method is not really taught anymore because we just learn, unless you have a geometric, unless you take a lot of geometry courses, we just typically memorize these things. But there's actually a relationship with these number lines and understanding that this is what linear means, that we're moving in values of plus, we're moving in absolute terms. Every single distance is plus 2. It represents the same amount of distance. This amount of distance is the same as this amount of distance. Same here. Here's plus 3. Let's do another plus 3. We get to 9, right? I don't like sometimes how this pin works. But anyways, look at this. This distance is the same. This distance from here to here, from 3 to 6, is the same as 9 to 6. It's exactly the same in a linear sense. So we say, well, what about something? Let's go to another example. Let me find a clear spot or just erase some stuff. So let's move on. Let's move on up. Let's move on up in the world. So our next question is like, well, is there another scale? Is there another way to do this? Well, what if we said, now you're thinking, let's have 2 to the third. Well, let me go back here. 2 to the third. 2 to the third should be pretty simple to write out. So we say, I know how I can rewrite this. We can rewrite this as 2 times 2 times 2. That's the same thing as 2 to the third. They both will give you 8. Okay? Because 2 times 2 is 4, times 2 is 8. And everyone's taught this. And so it's like, okay, how can we relate it to this though? Well, this one's different. Here we went from multiplication. Let me underline it. We went from multiplication to addition. Well, over here, we went from exponential to multiplication. And from multiplication, we can get to addition. But we've sort of stepped up our game here. Now we're working in multiplication. How would 2 to the third, what if we started with this and said, do this on a number line? We don't want you to break it down to multiplication and then break it down to addition. We want you to stay in the multiplication world. Well, you say, okay, well, let's see what we can do for you here. So let's draw out a line. So here is a line. And then so we say, okay, well, we know that we are moving in distances. This thing is the same as a distance of times 2, times 2, times 2. So we say, okay, well, here's 2. Let's put 2 there. We're starting with 2. This is the same thing because 2 to the 1 is just 2. So here's 2. So this is like 2 to the 1. And then we say, okay, well, we're going times 2. So this will put us at 4, right? And so we say, okay, well, again, we're doing times 2. That'll put us at 8. And we say, well, hold the phone. This is a different story over here. So this is 2 squared, and this is 2 cubed. And so we've rewritten this. We've now found the answer on a number line. We found the answer to be 8, and we know that that's true. But we noticed something here. We noticed that this distance is not the same as this distance. Not same. This one and this one. This distance is a distance of 2. This distance is a distance of 4. What the heck? This is where logarithms come into place. Logarithms and exponents are tied together. They are like the way multiplication and division is tied together. Same way. So these are very, very similar. So here we have times 2 times 2. So, that's very interesting. Let's do another one. So we notice here that our values get quicker much faster, and they've been related by multiplication instead of addition. This is a logarithmic or exponential scale. They are the same, very similar to the way multiplication and division are related. So, okay, let's look at another one. Let's keep it rather simple. So we'll do 2 to the 5th. I'm hoping I can remember my powers of 2 here. So here we've got another number line. And so we say, well, okay, here's 2. Whoops, I have my shape tool still on. 2 to the power of 1. And then we have 2 to the power of 2. So we moved in a distance of times 2. And we know that this is 2. This is 4. And then let's go ahead and fill out the rest of our table. We have 2 to the power of 3. 2 to the power of 4. I'm going to extend our line just a little bit further. And 2 to the power of 5. And if we were to evaluate this, we'd have 4. Well, this would be 8. Whoops, let's keep it blue. 8. And then over here we have, times 2 is 16. Times 2 is 32. Oh, yeah. If you get a bit higher. But we notice that these are unequal distances, but they're moving in times 2, times 2, times 2. And so now we are able to express ratios of numbers. Now this works fine for integers. So we notice these are not the same, but they are all the same multiplicatively. Same multiplicatively. And this is very important to us. What do we want a number in the middle though? Like what would be in the middle of this? Well, that'd be 2 to the 1/2, right? The 2 to the 1/2 will be in the middle of a multiplicative property. And this is a problem. What's that? Well, that's the square root of 2. And now the square root obscures this relationship here. It obscures the line that we're working with. The logarithmic nature is hidden by the square root, so it's kind of confusing. Now we've been talking about exponents. Let's go back to logs. Well, okay, here let's write out our equation again. So we have log base b equal to x. And so we're saying, when we say log base b equal to x, we're saying, let's go back to our number line. In fact, let's work up here. So log base b equal to x. The base b, this base, is our step size. Step size. That is our base. So since times 2 is our step size, we're moving in times 2. If we were moving in times 3, well, then we'd start with 3, and we'd end up with 9, 27, 81, so on and so forth. And our base would be times 3, so it would be log base 3. If there's no base written right, we just say it's log base 10. And we like 10 because 10 is very easy to move in. Because let's think about powers of 10. Here we have like 10 raised to, the second. Well, that's the same thing as 100. And on a number line, it would be very simple to work with because we have this great relationship here. Here's 10, here's 100, and we've moved in a power of times 10. And this is the reason, this sort of clued people in. If we have 100 times, 1, 2, 1, 2, 3. You know, what is this? Well, we can add the zeros, right? We have 1, 2, 3, 4, 5, 6, 7 zeros. So we can just put a 1 with 1, 2, 3, 4, 5, 6, 7. My commas are off, but you get the idea. This would be the answer. And so we can just add our zeros. So by moving in logs, we sort of come up with a similar shortcut. That's where the other way of understanding logs comes from. But we're not quite done yet, right? We've got our base. But how does this work? So what we're saying here is this is our step size, right? This is our times 2. So if we have log, so let's look at stuff. The way I was taught logs, so log base b equal to x, as I was taught this sentence, and the sentence went base power in equals out. And some people memorize emotion. They'll be like, oh, base power power in equals out. And what the emotion will look like, it'll look like it's base power out equals in. You should memorize your sentence correctly too. Base power out equals in. Okay, says I'm like drawing the motion. See, the motion is very useful. So it's like this b to the power of x equals whatever's on the inside of this function. So there's going to be some argument a, let's call it. So if we had like log, we know that log of 2, 3 equals 8. And so what is that saying? Or I have this backwards. Log of 8 base 2 is equal to 3. And we're saying base, which is 2, power out 3 is equal to 8. That's what we're saying. And on a number line, what we're saying is here we have the value of 2. Turn off the shape tool. Here we have the value of 2, and then times 2 3 times. 4, 8 times 2. Because this is 2 to the 1, right? So there's going to be 2 times 2's because there's 2 to the 1, which would just be 2. If we started off at like 1, here's like the number 1, and we went another times 2. Then we would wind up with 8. And so we say, hey, this is really interesting. Why do we care about this? Well, what we're doing now, so let's talk about how the two scales are related. So what we can do with this scale is we can take, let's present the problem now. Yeah, this was all just sort of a warm-up to an explanation. So, okay, now we have this pretty good idea. We got these number line things in our head, but what's going on? Well, let's say we have a scale. Let's say we have some scale. And we have here, we want to express our scale. And so we say, okay, well, here is 1. Let's call it 0. Let's call it 20, actually. Let's use a real scale. So this is the audio scale. We can hear from 20 hertz to 20,000 hertz. But there's a thing about the way we hear. There's a problem, and that is that we hear octaves as a power of 2. And so that means that if I play for you a note that sounds at 440 hertz, in order for you to hear an octave up, that would be 880 hertz. I'm sort of banking on you knowing what an octave sounds like. But if you were to play like on the piano, we know that there are 12 keys, right? There are 12 of them, and they repeat over and over and over. And these 12 keys, they look like, here's C, and then we have D flat, D, E flat, E, F, G flat, G, A flat, A. And these are the black keys, boom, boom, boom. And then we have B, and then our keys repeat. And these keys on the piano, there's one more black key here. 1, 2, 3, 1, 2. And they repeat on and on and on, right? And they represent the same amount of distance. But we can express them in pitch, which is, here's C, D flat, E. Just so you know, they're like the names of the notes on the piano. And this C is the same as the C up here. It's just an octave up. And so we say, okay, well, this is really interesting. You don't see the keys stretching out. You don't see keys getting bigger or smaller on the piano. They're the same all the way up and down the piano. But the Hertz value that the keys represent. Now it gets kind of complicated because there's physics and stuff, but the Hertz values change at a ratio. They change dramatically. This C could be 440 Hertz. This is actually an A, but we're just going to ignore that because, just cause. So let's just say for whatever reason, we're calling it C today. And so we have 440 Hertz. Well, if we move up an octave, this would be 880 Hertz. We see that this distance is times 2. However, we know that this is the same amount of distance. But if you were to draw the keys again, the next one would be 880 times 2, which this distance would have way more Hertz, which is like the more scientific way of sort of looking at this. But the pitches would remain the same. So here we're relating, because we hear logarithmically, we are relating Hertz and pitch. The same problem comes up with dynamics. And so let's go ahead. Well, let's look at this. So this is all sort of, let's look at this 20 Hertz and 20,000 Hertz. And let me erase a bit so that there's not so much confusing mumbo jumbo on here. So, okay, that's all well and dandy, but let's move on to the next level. Well, let's say, okay, let's map Hertz on, whoops, gotta turn off the shape tool, Hertz on an absolute scale. So here's 20,000 Hertz, here's 20, here's 20,000. So in the middle, on an absolute scale, the middle would therefore be half. So that's 10,000. And so let's do half again. Well, let's zoom in here. So, okay, this is 10,000. So that means the half would be 5,000. And half of this would be, I don't know, some number. It would be, what is that? 5 divided by 2, 2.5. 250. Yeah, 250. That would be 500 Hertz. 2500. And then so on and so forth. We continue chopping into values of half and half and half. Now, this is on a linear scale. We just keep getting smaller, smaller, smaller. We notice our distances shrink on linear. Well, this is a problem because let me point out to you this problem. Well, here's 20 Hertz. And well, let's just pretend this is 40 Hertz. This is 20 to 40 Hertz. This itsy bitsy distance is 1 octave, right? And there are 20 Hertz in this octave. But we hear the same 12 notes in this octave, not very well, but they're there. 12 notes are in this octave. Well, up here, boom, this whole space is 1 octave. And we hear it the same as this itsy bitsy distance. And this 1 octave also has the same 12 notes. Now, there are actually systems that take advantage to the fact that there are more Hertz values up here. But there's actually 10,000 Hertz values. Whereas down there are only 20. So we have all these interesting problems about tuning and stuff that I could begin to bring up, and all these extra things that are actually really cool to understand. But our fundamental problem is this. This is a linear scale, and linear. And linear scales don't work for this sort of a thing. We don't like this. Linear scales are useful for being very specific, but they don't work. Another thing about linear scales is they are very unuseful. Not useful. Let's just say not useful. Not useful for communicating music, because no one's going to say, hey, play 440 Hertz. No one's going to say that. They're going to say play A. And they could mean any A. They're all the same to us. They don't mean play like A80. Now, we do tune to our Hertz value, and there are a whole bunch of really cool reasons that I could dive into. But the point is, we have a useful, a better way of expressing this, because we could say, hey, play 5,672 Hertz. It's just too random of a number. And so it's better to just say, like, I'm not saying this was that Hertz value, but we could just say play C or whatever. And there are places for each of these scales. But we will often translate for the purpose of what we're trying to communicate. So if we're trying to communicate, harmony, working in Hertz values is a bad idea. But there are other benefits to working in Hertz values. It gets kind of confusing. When you get into more advanced harmony and stuff, you'll begin to look at Hertz values and look at the problems they present. But generally, this is just not good for communicating certain information. So let's go ahead, let's erase some, and let's look at the power of what we're going to do here. So let's erase all this. Okay, so let's do the same scale, only now let's work on here's the same scale. Let's work on a value, a logarithmic value. Let's work in a logarithmic value of base 2. And so that means that our step size is 2. So if we're at 20 hertz here, and here is, 20,000 hertz, 20K, and these are in hertz values, well, let's make it look more like the music we're familiar to looking at. So here's 20 hertz. Well, that means that a distance, this probably isn't going to work from the scale. We're just going to work from the bottom up. So let's say that this distance is times 2, right? So because that's our base, well, the 1 octave now, 40 hertz, is represented by this space. Now, instead of this, we're moving in multiplication. 1 octave represented by this. Times 2 again, we get 80. Times 2 again, we get, this should be 80. So this is still 1 octave. And then we get times 2 again, what is that? 160. And then we get 320 or something. So on and so forth. And we can actually hear 8 octaves, at least I believe, off the top of my head. I could do the math right now and figure it out. But now we're moving in times 2. This is logarithmic. We're moving in a log of base 2. And what we can do is we can actually find values somewhere in the middle here. We can find all these middle values by using logs. But before, our scale was very squished. And now our scale is more linear, and that's the way we actually perceive a lot of things. We perceive distances this way, color this way. There's just a lot of things we see in a logarithmic fashion. They might not all be the same. They might have a different base. But this is the big thing I want to point out about logarithms. This isn't necessarily a solving logs video, but a lot of times solving logs is just a matter of getting things to the same step size. So this is a very, very important thing. I'll probably do some examples of solving logs in another video and reference this video just for understanding, because understanding that you're moving in this looks like that should be a multiplication value, but whatever. Understanding that you're moving in multiplication and that there are useful applications that this actually comes up in, such as the dB or the hertz to pitch, is very important. And understanding that why these things take place and having a visual sort of to go with it just made the world a difference for me, so that when we move in logarithmic values, it totally makes sense. It also helps. This is like calculus, but if you're dealing with integration, and up here is x squared and here is x, this suddenly you're changing the scale change, and you're changing the way you're taking the scale. And when I just finished calculus 1, so I'm not some expert on this, but I got an A. And understanding that I was one of the few students who understood this. I'm sure there was more, but most of the students just memorized these abstract properties, and it's just not the way to go about doing math. They didn't understand what things looked like or what it meant. They just knew how to get the answer. More emphasis on understanding, I think, is given in higher maths. But yeah, so this is a very nifty way of understanding logs. And so that's that. I'll probably fill in this video with a couple other videos explaining more practical examples. But when we're doing things with logs, algebraically, that's what's going on the number line. So versus now, if we go back to our beginning, we say that, some log base b with some argument a is equal to x is the same thing as saying, so now we can understand this way better. So now we can say, okay, well, this is our step size. This is the number of steps. It might be some fractional value. It might end up in the middle. Who knows? Some decimal value. They tend to turn out like that. And that's actually the original. Well, I'll explain that after. And then we have A, which is where our number of steps will take us. All right. So let's say we have log base 2 of, let's say 8 is equal to 3. Okay, well, let's draw this out. So here we've got it. I know I keep using the same example because I feel like consistency, just understanding what this means will allow you to understand any problem. So here we have, so log base 2. So here's 2 to the 1, 2 to the 2, 2 to the 3. And then we're saying that, hey, we now notice that this is relating. This is the big power of logs. Logs relate multiplicative and absolute scales. So here we have if we look at this, here's our powers are moving in plus 1, plus 1, plus 1, plus 1. Okay. And so that's a 1, 2, 3. This is a linear scale. Linear. But we are moving in a logarithmic scale. So they're relating the scales. That's just another thing I want to point out here. But we now see, oh, log base b. And then we have some number of steps. So we have 3 steps. So this can be seen as linear. This is our linear scale. This is how our linear scale fits into this. Linearness happens here. And then we say, oh, well, this winds up at 8. This is where the logarithm comes from. That's why we say we take the log of some number a, and that will give us a corresponding value on a linear scale. So if we take the log base b of some number a, will give us some corresponding linear number. Corresponding linear number. And so now we can see, hey, these are relating linear and logarithmic scales, and that's why it allows us to go from Hertz to pitch. So that's really useful. I hope this made sense to you as far as logs go. As we do examples, it becomes more and more clear as you do, but just understanding, hey, this is the relationship that goes on. Super nice to know. If you have any questions, let me know. Subscribe, support me on Patreon. I plan to do more of these videos, more math videos, because it's underlying in so much of music and physics and a lot of physics. But if you understand it, it just gives you such a leg up in sort of knowing what you're doing, especially when we get into DSP. Like this explains why we, go from Hertz to pitch. That's explained in this video. There's a number of other relationships that go on. Subscribe and have a blessed day.